your gradation distributions. As I mentioned in our first lecture, the first 4 topics that we're going to talk about is very applicable in the industry, but very intuitive. If you don't understand this or have this present in your mind before we move forward to topic number 5 and later on, you'll get lost. In fact, I remember several of the students were joking with me and say that the level of complexity or the challenge of the course starts like this and then goes nosebleed. So you have to be careful with that. So you have to be very careful with the definitions. A lot of times you might sit in the class and say that, well, I understood what's going on, so I probably will be in good shape. But if you don't revisit the material, it's going to be problematic. Now that we're talking about this and we have some time, let's go to talk about this one as well. At this point, you guys are all professional students. You probably sat behind those desks for, I don't know, over 15 years at least, right? So what happens in the retention, this is the theory of education that might be useful, in fact, Alex. It would be interesting to think about those when you're looking at reading the material. You typically have about 6 hours from the time of your first exposure to the material to the review. If you don't review the material within 6 hours, you come back and look at it 2 weeks afterwards, it's all new material. There should be connection between the short-term memory and long-term memory. You need that 6 hours. I'm sure that all of you are extremely smart people, but this is the way that the brain works. You have to establish those mental connections. If you don't revisit the material within 6 hours, you will not remember that. That's how the human evolutionary mind works, right? So let's keep that on the side, but let's move forward with what we are talking about in terms of soil. All right. So we have coarse grain material and fine grain material. We'll look at sieve number 200, and we look at materials that are smaller than 75 micron and larger than 75 microns, right? So we have said for the soils, we're essentially looking at the mixtures, right? So we are looking at mixtures with more than 50% fines in it. You call that material to be fine grain. On the other side, if you're looking at material that has more than 50% retained in sieve number 200, you call that material to be coarse grain, right? The engineering behavior of coarse grain material and fine grain material are essentially very different from one another. We're going to talk about those, and we're going to see how we can characterize those in the lab and also in the field at some point. All right, so let's get back to our discussion. We talked about the coarse grain material, and the parameters that influence the coarse grain soils are, Esteban? It's a little late to go through that right now. We should do it before the class. The parameters and properties that influence the coarse grain material. What's that? Particle size. Let's start with the first one that we talked about. We're looking at particle top size, or the maximum aggregate size present in the noise. Right? So that's the one that is of great importance. The larger would be the particle, the higher would be the stiffness properties. That's the way that you can essentially correlate the two with one another. What was the second one on the list?
Particle size distribution.
Particle size distributions or the gradations. Remember we talked about the different types of gradations that we have, right? We have well-graded material and we had poorly graded material, right? So that was basically the general definition that we have in terms of the gradations. So hopefully today we talk about how you can mathematically determine if you had an elongated S-curve or a short S-curve, or you have that gap gradation. All right, in terms of the types of gradations, what types do we have under the poorly graded gradations? Right, we have uniform gradations and we have gap gradations, right? So for uniform gradations, those are consisted of similar size particles, right? So uniform gradation, remember uniform, remember we talked about the connotation of that. Uniform, when we say something is uniform, that probably the thing that comes to our mind is that it's a good material. But remember what the good means in geotechnical engineering. It could be related to the stiffness properties, or it could be related to the hydraulic conductivity of the soil, right? Permeability of the soil versus stiffness properties. Basically, you have to strike a balance, or you have to figure out what exactly you're targeting. Remember, we talked about if you're looking at the foundation of this building, you're looking at stiffness properties, right? You want to make sure that you have a robust platform to build your foundation at the top of that and build your structure at the top of that, right? So that's basically what it means in terms of the robust platform. For that specific case, what kind of gradation would you choose? A well-graded material consisted of larger particles, right? Again, let's go back again and revisit what we talked about in terms of the gradations. Remember, we are talking about well-graded material are gradations that consisted of large particles, intermediate particles, and smaller particles. The concept was, I want to maximize the density. What's the definition of density, or how you calculate the density? So you're basically looking at a measure of weight and a measure of volume, right? Weight over volume. Assuming that I'm looking at constant volume, meaning that I'm looking at a rigid mold, a rigid cylindrical mold with constant volume in there. I have to have small, intermediate, and large particles to basically maximize my weight that I can pack in there. In other words, I want to have those small particles that go in between those cavities or gaps to provide larger weight, right? So that's basically the concept that we have there. So once you have higher density, then the way that you have to think about it is in terms of the load distribution mechanism in particulate media. What was it? What's a particulate media? It's a medium that is consisted of particles, right? That would be our soil. Essentially, I'm trying to differentiate between what you have in concrete, wood, and steel, as opposed to the soil, right? So these are particulate materials. The load distribution in particulate soils was associated with friction and interlocking effect. That's extremely, extremely important. I would suggest that if you didn't write that down, write it down somewhere. We're going to revisit that periodically in this course. Load distribution in particulate media, in parentheses, soil, is through interlocking effect and friction. So the higher would be the interlocking effect, the higher would be the stiffness properties of my soil. Right? So that's basically the direct consequence of that expression. So let's go back and take a look at that in terms of what we talked about in terms of the stiffness properties of the platform here. So we are looking at foundation of this building. By the way, what is a foundation? Right. Foundation is essentially a structure that transfers the load of your structure to the weakest link, which is the soil. Right. That's basically what we have. So we have this big, huge structure. Do you think I can just place this structure at the top of the soil without having any medium in there? We can't, right? So you have to have a medium, such as a concrete platform, to be able to reduce the stresses that your soil can tolerate, right? And that was the operating word. Reduce the stresses that your soil can tolerate. What kind of stresses can the soil tolerate? Very small magnitude stresses, right? As opposed to concrete. Again, this comes from the concept of materials. You're familiar from your materials class that you have a concrete slab, high modulus value, therefore, under loading conditions, you will see small strains, right? Or the deformations are going to be minimal, going to be small. On the other side, if I have a soil layer, uncompacted soil layer, as soon as I put my foot at the top of that, you see the deformation will take place, right? So that has to do with the magnitude of the stresses, but the way that you have to think about it is in terms of the stiffness properties of the layer. You know that the stiffness of the soil is much less than the stiffness properties of the concrete, right? So, going back to our discussion, I have foundation. Foundation is consisted of a concrete platform. Typically, it would be a reinforced concrete. Reinforced concrete meaning that you have the plain concrete plus some reinforcement of steel, right? So you do have the steel in there that compensates for the low tensile properties or improves the flexural strength of your concrete. On the other side, you have plain concrete, which is excellent in compression, right? So you have the combination of the two, and also what happens is that as soon as you put the structure at the top of that foundation can transfer the load to a tolerable level for your soil, right? So that's basically the general concept that we have. And I mentioned the word weakest link, right? Because if you're looking at the materials that we have, you have concrete, you have steel, you have masonry materials, you have wood, all the different types of material that we have. Soils are typically of lowest modulus values or stiffness properties. And that's the reason that you have to bring the stresses to a tolerable level for your soil. Otherwise, you might have designed the best structure, the most robust structure, but if the foundation gives way, what happens? Everything fails, right? And for geotechnical work, for civil engineering practice, pretty much everything that we build in one way or another deals with soils, right? So think about it: residential building, commercial buildings, bridges, what else? Highway pavement, airfield runways, dams, hydraulic, any type of hydraulic structure. So anything that we deal with essentially has to do with characterization of the soil. So if you learn the soil part, you probably have some job sometime, right? Because every structure requires a geotechnical person to be involved. Now talking about that, geotechnical engineers are the most engineers that get sued. So you might want to consider that one as well. All right. Because when something fails, as soon as they start figuring out what went wrong, they start from the bottom, right? Start from the geotechnical engineer and go all the way. All right, so with that in mind, let's go back to our discussion about the gradations. We were talking about dry sieve analysis, right? So for the coarse grain material. What was the dry sieve analysis entail? Well, this is something that you have prepared yourself, hopefully, for the lab, for those of you who are going to the lab today. So essentially, dry sieve analysis means that you have dry material and place them at the top of assorted meshes, right? So assorted meshes, you basically have the one with the larger eyes or larger openings at the top, and progressively the sieves becomes finer and finer as you go down the stack. And at the very end, you have a pen, right? Which basically collects the material that passes sieve number 200. The last one that we have is sieve number 200, and the particle size correspond to that is 75 microns. Hopefully, when you leave this class, you remember that number. 75 micron or 0.075 millimeters. Right? So that would be the particle size that we have. All right, so you collect the material at the pan, in the pan, and then you measure the weight on each of these sieves, right? And we're going to talk about how we can establish your Excel spreadsheet to be able to properly plot your gradation curve. But in previous lecture, we talked about two things about the gradation curves. We talked about the gradation distribution. We looked at the cumulative distributions, and also we looked at the histograms, right? So remember what the histogram was? Yes, so basically the histograms essentially shows you or is a visual representation of the frequencies in each cluster, right? For us, frequency would be the weight that retained on each sieve, right? And what is the cluster? It would be the particle diameter. So that's basically how the general definitions in your statistics correlates with what we are talking about here in terms of the geotechnical. All right. So we looked at the histograms. We looked at well-graded material. The distribution looked like a bell curve, a very well symmetrical bell curve, right? On the other side, we looked at uniform gradation, which was a short bell curve, right? And ultimately, we looked at gap gradations, which basically tells you that we have concentration of mass or particles in certain size bins and lack thereof in some other bins, right? And for that, you typically see a bimodal distribution there. So those are the definitions, or those are the distinctions that we have in terms of the distributions. We talked about the application of each, so quickly remind me what the applications are. For well-graded material, this is what we talked about here, right? So any place that you need stiffness properties, right? So think about it in terms of the stiffness properties. It could be foundation of the building, it could be the base layer of highway pavements, it could be the supporting layers of a precast concrete slab in your airfield runways, anything that requires weight management. Not that weight management, the weight of the structure as well. All right, so what else do we have? We have uniformly graded. In terms of the uniformly graded, the example of that would be
Drainage?
drainage layers, right? Again, the way that we have to think about it is in terms of the gaps or cavities in between the trapped particles, right? Between the particles there. The ones that have larger gaps allows for the transference of the moisture a whole lot easier compared to the ones that they're tightly packed, right? So this is another way to think about it. All right, so thinking about developing a moisture barrier, do you use a gap graded, uniform graded, or you use a well graded? Probably a well graded, right? Because you're looking at reduction of the voids. Reduction of the void content, therefore that's how you can control the permeability. Later on when we talk about the applications, we'll see that probably looking into non-plastic seals in the core of the dams would be a good material to use for creating a moisture barrier there. But let's keep that in mind for now. Any material that provides lower void content, lower interconnected voids, remember we talked about that, lower interconnected voids as opposed to the isolated voids, right? Remember we have two types of voids in civil engineering structures. All right, so those were the things that we talked about before, and let's get into a new discussion, and that's related to the geometry of the particles. Right? We talked about the particle topside, we talked about the gradations, and now we want to talk about the geometry of the particles. All right, so remember in our first lecture when we talked about the different types of characteristics of soils, we talked about stress sensitivity, non-linearity, non-homogeneous material, soil has memories, and anisotropy, right? And the one that we are going to talk about today is related to the anisotropic behavior of the material. What is anisotropy? Directional dependency. Yes, it basically is the directional dependency of material properties. It's a directional dependency of material properties. What does that mean? It is, in very simple terms, it means that the stiffness properties in horizontal direction is different than the stiffness properties in vertical direction. In very simple terms. In fact, what I just described is the definition of cross anisotropy. Cross anisotropy essentially means that you have two modulus values, essentially Ex and you have Ey, and your Ex is different than your Ey. Very simple terms, right? It's coming from your continuum mechanics. So anisotropy is the directional dependency of material properties, and I want to tie this to the geometry of the particles. The way that you can characterize the geometry of the particles is through three parameters. You're going to take a look at the equipment that we have downstairs, and there are only a few universities in the US that have that. It's called the aggregate imaging system. We purchased it about 5.5 years ago, and I'm going to get into that. That's extremely interesting equipment. All right, so let's call it aggregate geometry. You can subcategorize the aggregate geometry into particle form, the second one into particle angularity, and the last one would be the particle texture. All right, so let's talk about each of these. Particle form has to do with flat and elongation. Flat and elongation of the particles. Let me just quickly define these and talk about how they are going to influence the behavior. Particle angularity has to do with the broken edges of the particles. And particle texture has to do with surface macro texture. All right, so let's define and talk about each of these and see how they are related to the stiffness properties. All right. Hopefully for the last time, tell me what is the load distribution capacity, or what is the load transfer mechanism in soils? Through friction and interlocking effect. So keep that in mind. We want to basically tie that concept to what we have on the slide. All right, so we are looking at the particle geometry. And the first one is called particle form, which has to do with the aspect ratio of the particles. In very simple terms, I want to see what is the aspect ratio, meaning the length over the height that we have. Very simple terms. So we are basically looking at flat and elongated particles as opposed to equidimensional particles. Right? So think about it in another way. We are looking at spherical particles or cubical particles. Those are one equidimensional, right? As opposed to very flat particles. So let's take a look at two systems together. That probably would be more understandable to describe in terms of the behavior. Let's assume I have system 1, which is basically consisted of flat and elongated particles. And these are my flat and elongated particles. The second system consisted of equidimensional in 2 dimensions square particles. In 3-dimensional would be cubical particles. All right, let's call this one system number 1 and call this one system number 2. All right, let's get back to our discussion again. We are looking at air particle frictional properties. What is the friction a function of? Statics. 2315. How do you calculate how do you calculate friction? You need to know the normal force and you need to know coefficient of friction, right? So your coefficient of friction is going to be tied to the surface, right? In other words, if I have 2 points that are touching, or I have 2 large areas that are touching each other, right? So these 2 larger areas essentially provide better frictional forces as opposed to 2 points. Make sense? That's very simple. All right, so this would be the flat and elongated system. What is the surface area that counters the force, counters the vertical force in this situation? Let's assume that I have, this is my loading condition, this would be my P here. What is the area that resists this load? The area is going to be where those particles are touching each other, right? At the top of one another. How about if I have a horizontal force? You have P happening from the top and you have 2P happening from the horizontal direction. What is the area that counters the 2P?
Where they contact.
Right, those are going to be the surfaces that are going to be perpendicular to the direction of the load in each case. Do you agree with that? So the thing that you have to think about is, in vertical direction, I have to see the area that is perpendicular to the direction of the load. And it's going to be much, much higher compared to the horizontal, right? Do you agree with that? This system is extremely, extremely anisotropic. Meaning that under these loading conditions, when I have a lot of flat and elongated particles, this system is prone to shear rutting. shear deformation. Now think about it in terms of system number 2. Do I have similar distribution of the particle contacts in 2 directions? Yes. Now if I have P happening from the top and P happening from the horizontal direction, P here, P here. This system is as close to isotropic situation as possible. Equidimensional particles and similar loading dimensions. For those of you who are interested in this topic a little bit in detail, this is, you can subcategorize the anisotropy into 2 main categories. One is called inherent anisotropy, meaning that it's shape-induced anisotropy. It's related to the shape of the particles. The other one has to do with load-induced anisotropy, and exactly what I did there. I put P there and put 2P on the horizontal. So my loading conditions are not the same. But on the other one, you have hydrostatic or isotropic stress state. Isotropic stress state, and again, from the mechanics of materials, essentially the stress state with similar intensity in different directions. And that's what we have there. P from top and from the horizontal. But the one with the flat and elongated, essentially we don't have that behavior there. Where do you see this? This kind of behavior.
Clay.
Think about it in terms of the applications that we have. Where do you have a lot of horizontal forces in structures? Wind could be one, yes. Anything that has to do with the horizontal forces. What else can you think of?
Seismic.
Seismic would be another one. Excellent. What else? Any place that you have high changes in the deceleration. Where do we have that? Highways? All right, let's think about this. You're driving fast, hopefully within the speed limit. And then you see the traffic light turns yellow and turns red immediately. What would you do? You step on the brake. Right? You step on the brake. So what happens to the surface of that asphalt?
Shears.
You see a lot of shearing forces. Right? Now think about that. Next time you're driving, take a look at the rolling of the asphalt at the intersections here in El Paso. You see, at the intersections, you see a lot of corrugations, you see a lot of rolling of the asphalt. Right? And this is the mechanism for it. Because people are stepping on the brake, there's going to be a lot of shear forces developed between the layers and the surface, and then the asphalt layer will rub. We're talking about the asphalt. Think about it in terms of hot summer days in El Paso. High temperature, right? What happens to the modulus value of your asphalt layer? Asphalt is going to be softer, right? And then you're going to overstress it by stepping on the brake. Maybe your car and my car is not going to induce that much damage, but if you're looking at a heavy truck, that's going to induce a lot of damages, right? Because the weight is going to be... Now that we are talking about the highways and pavements and runways, can you tell me another example of shearing forces?
Same concept.
All right. Roy says when the airplane lands. All right, so what happens at the time of landing? Basically, we'll see a lot of impact forces. Your concrete layer is going to be very well taking care of that. And if you have surface layer, which is going to be an overlay of asphalt, underneath that is going to be concrete slabs, we're going to have load transfer devices that are going to help for slab number 1 to transfer loads to the slab number 2. We call them the load transfer devices. If you're interested, pavement design, to talk about that in detail. But it's a little bit counterintuitive. In fact, at the time of takeoff, the magnitude of the loads and the magnitude of the shear stresses are going to be a whole heck of a lot higher at the time of landing. Why? because you see the airplane is taking off. There's going to be a lot of shear forces developed between the layer, and the weight of the aircraft is going to be higher at the time of takeoff than man. Why? Because of the fuel weight, right, at the time of takeoff there. So if you look at the analysis of airfield runways, the critical stage would be at the time of takeoff, not at the time of landing. So that's going to induce a lot of shear stresses in between the layers. And you think of another mechanism.
Inclined surfaces.
Roller coasters. Yes. Excellent. That's very good. Not a civil engineering structure, but that's a good one. Can you extrapolate that into civil engineering structures?
I guess like the force of, I'm thinking when the ride comes down, like the pressure because of the weight, the curves on
The
the
curves.
soil.
All right. The operating board, the clue is curves. What happens in curves?
Constant celery.
Centrifugal forces? Yes. The centrifugal forces are horizontal in nature, right? Think about it in terms of Formula One, right? All those fast-moving vehicles on the deck. What happens? It induces horizontal forces and it results in the rolling of the asphalt. So these are the things, hopefully, you can think about it in terms of the different types of horizontal forces that we have. All right, getting back to our discussion here, we're looking at the form, right? So essentially what form does is that you're looking at the aspect ratios and you want to make sure that you're producing aggregates in the quarries that are equidimensional or as equidimensional as possible, right? Because we don't have control over how the particles break. We have a little bit of control over that because they're predominantly determined by the crushing techniques as well as the mineralogy of the so basically what they do in the quarries during the crushing techniques is that they change the gapping between their jaw crushers to create more equidimensional particles as opposed to flat and elongated particles. Because if you produce flat and elongated particles and use that in your mixture design, those are going to be prone to the shear deformation or the shear rutting as we described and talked about here. So does it make sense why we need more equidimensional? Because more isotropic systems are desirable, right? If you have too much of preferred orientation, this is the way that things will happen. So what happens if I have aggregate particles like this? When you compact the soil, right? You typically compact the soil. Under the energy of compaction, particles tend to align themselves with the horizontal plane. And this is exactly what happens. So that's the reason that you want to have equidimensional particles in there. So that was the first one, and that was particle form. The second one was particle angularity, and that has to do with the shape of the particles. Let's quickly take a look at two systems here. Let's assume I have a siliceous gravel sourced from a riverbed. And you have crushed granite sourced from Virginia. Crushed granite material sourced from Virginia. The reason I put Virginia is that they do have very good quarries with good quality of granite material. Unfortunately, we don't have much of that here in Texas. And then we have siliceous gravel sourced from the riverbed. Angularity has to do with the broken edges of the particles. Which one of these two systems provide better interlocking? The crushed one, right? So you need to have crushed materials to provide good interaction between the solid grains to improve the stiffness properties. This is again how you have to think about it. Anything that we talk about here, you have to see how it's related to the friction and interlocking, right? So anything that we talk, see if you can draw parallels with stiffness, interlocking, locking together, providing good friction. Right. All right, so this was particle angularity. And the third one on the list is particle texture. Right. Particle texture, this is very intuitive, right? You're essentially looking at surface macrotextural properties. The more asperities are on the surface, the better interlocking between them. And therefore, they lock better together, they provide better frictional forces. We might have talked about this previously. Remember the two ends of the spectrum? You can think about it in terms of two very smooth surfaces, such as two mirrors that are sliding past one another, as opposed to two sandpapers. Right? So two sandpapers, that requires a whole lot more force to mobilize those two past one another. On the other side, if you have two very smooth glasses with a little bit of moisture in between, they easily slide past one another, right? So low friction properties against high frictional properties. All right, we do have an equipment downstairs, and it's called Ames Aggregate Imaging System, and you're gonna take a look at that and take a look at some of the results and figure out if you can determine the form factor, angularity factor, and textural properties of a representative soil layer. We do have some other tests in offshore. It's called the flatten elongation test. And the whole premise of that test is that you make sure that you're not putting too much of flat and elongated particles in your mixes. With too much of those, you know what the consequences are. Lower stiffness properties, but probably the most important one is that you basically have high level of anisotropy. Right? The way that you can think about it in terms of the level of anisotropy is that you're looking at the differences or major differences between the horizontal stiffness and the vertical stiffness. Right? We want to minimize that. And on the other side, you as designers, the way that you have to think about it is that the more isotropic the system is, the easier it would be to design it. Right? Again, the reason for that is lower complexity and at the same time higher reliability in your design. Because if you have too much of complexity there, that basically counters the reliability of your design. All right, any questions here? All right, so let's move forward and talk about our lecture slides. We can move quickly. I'm going to post these lectures hopefully after the class so you have access to that as well. So we're going to quickly go over some of the materials that we talk about and see how we can characterize the gradations. A lot of the materials that we see here is something that we talked about it, so we can quickly move forward and see how they would look like in terms of the gradation distributions and their contribution to the stiffness properties. All right, remember we talked about the soil texture. Soil texture in very simple terms, it was how it feels when you hold it in your hand, right? So once you hold the soil in your hand, the things that comes to mind are particle size, the assortment of the particles, small, intermediate, and large ones, right? And ultimately, the shape of the particles is another thing that comes to mind. If it is a siliceous gravel, rounded ones, as opposed to crushed ones. Thinking about that, all Federal Highway and TxDOT or any Department of Transportation will not allow you to use materials that are rounded for load-bearing layers unless you do some sort of mixing and be able to essentially convince your state supervisors that you can use that. But essentially, it's not a good idea to do. In terms of the qualitative look at the particles, you can have rounded, sub-rounded, and crushed aggregates. And as we talked about, we are interested in materials that are crushed because they provide good interlocking effect and the whole jazz. All right, let's go back to the grain size and the definitions of that. We are looking at fine grain soils and coarse grain soils. We talked about the important sieves. The sieve, the first sieve that you have to look at would be sieve number 200. Particle associated with that would be 75 microns. On the other side, if you're looking at coarse grain material, you basically have gravel and sandy material, and the sieve that separates the two is sieve number 4, or 4.75, as you can see here. This is based on Unified Soil Classification System, USCS. We have different ways to essentially classify the soils, and these are the different types that we have. The first one is USCS, and probably if you start working in the field 95% of the time, that would be the one that you're talking about. The other one would be the AASHTO soil classification. If you work in pavement industry, or you work in airfield and runway industry, you basically will also have to be fairly familiar with what AASHTO classifications are. The third one is the MIT one, Dr. Whitman and Lamet book. The last publication that they had of their very, very good book was 1979. Probably a lot of people in this room were not even born at that time. But that's a very good book. It's out of print, but they call it the MIT classifications. Even the MIT folks don't use that anymore. So it's good there for just references. So the main ones that we look at are USCS, or Unified Soil Classification System, and AASHTO Soil Classification System. Once we start talking about the classifications, hopefully in 3 lectures from now, we're going to revisit this plot again. But let's take a look at the differences between the USCS and AASHTO. Remember that we are looking at coarse grain and fine grain. For the fine grain, we look at silt and clay, and for the coarse grain, we look at gravel and sand, right? You do have larger particles, as you can see there, pebbles and boulders, but let's put them aside. All right. Notice that for the case of USCS, we don't have any distinctions between silt and clays, right? As you see there, anything smaller than 75 microns, we just call them silt and clay. Later on, we have other tests to be able to differentiate. But here, we are basically looking at anything smaller than 75 micron, we just call them silt and clay associated with USCS. On the other side, for AASHTO soil classification system, you see that there's a distinction between them, right? For silts, material that fall in between 75 micron and 2 microns are called silts. Between 2 micron and 1 micron, it's called clays. And anything smaller than that is called colloids. So this is basically the definition that we have, and you have it on the plot here.
Why is it important to differentiate between silt and clay?
Oh, this is very important because of the surface area. We talk about that later on. Just quickly, let me just hit the main points there, and we can talk about the fine grain soils. For the fine grain soils, the particle size is really not as important as other parameters. Other parameters, or the most important one, is called the surface activity. And that has to do with the absorption of the moisture. The way that we characterize this is through the plasticity of the soil, right? We want to see how much moisture it can absorb, because we are interested in the volumetric stability of that fine grain soil, such as the subgrade soil, right? So if you have moisture that easily gets into the subgrade soil, and you have a type of clay or material that can absorb a lot of moisture, you see a lot of expansion and shrinking of the material, right? Also, if it goes through the freezing period, you know that, for instance, the moisture inside the cavities, when it freezes, it expands, and therefore it can create an uplift pressure that ultimately will blow up the pavement or your foundation there. So we have to be very careful with how we characterize the fine portion of the mix. Again, that's a reason that a lot of agencies, they limit the amount of fine that you can put in the mix, even if it's a non-plastic fine. If it's a plastic fine, they definitely have a cutoff value for that, and make sure that you're not putting too much of fines in the mixture. And you'll see later on that we have a lot of equations that specifically targets the clays, the material between 1% and 1 and 3 microns. But the behavior of silts are going to be different from the clays. We're going to get into that discussion hopefully later. All right, so these are essentially the particle ranges that we have in USCS and AASHTO soil classification system. Let's quickly go through the definitions together. You're familiar with this, we went through that, but it would be good to look at them a little bit more in a more organized way. We are looking at the mechanical sieve analysis. It essentially has to do with the determination of the particle ranges, and is expressed in percentage of the total dry weight. You have sieve analysis, that would be related to the coarse grain material. You're familiar how we do it. Remember, large particles and go progressively smaller and smaller in the stack. And then you mechanically shake it and make sure you measure the weight retained on each of those sieves. And then we have the hydrometer test, which is the test that we have for fine grain soils. And this is going to be the subject of your second one. We're going to talk about that hopefully in a second. But let's quickly take a look at what we have here. For engineering purposes, we categorize the soils into coarse grain and fine grain. Under coarse grain would be gravel and sand on the fine grain, it would be silt and clay. Depending on the classification system that you look at, you can just put silt and clay under the same umbrella, or you can separate it, right? The separation was the Ashto soil classification system that you have specific ranges. What do we need in our particle size distribution? You need to know the weight retained on each sieve. You need to know the particle diameter, right? Remember we had gradation curves. What did we have on the y-axis? Percent passing, right? What did we have on the x-axis? What did we have on the x-axis?
Log diameter.
Log diameter, right? That's extremely important. It's a log of diameter. And the reason that is important is when you start determining the gradation parameters, you have to figure out what the particle sizes is smaller than 10%, 30%, and 60% of the soils are as an input to the equations. And since it's not arithmetic, you have to be careful the size that you select there. We'll get to that. All right, in terms of the particle size analysis, we are doing it in 3 ways. Essentially for the coarse gradations, you're looking at mechanical sieve analysis. For fine grain soils, you can either use hydrometer test or you can use the laser scattering particle size analyzer. So essentially what that is that it shoots a beam of laser to the particles, and based on the angle of refraction, it gets an indication of the particle sizes. This is something that the majority of the time that they're using this one for in drug industry. So because they're dealing with the powders essentially. So this would be for the medical applications. The project that we have with NASA, we're going to use this equipment to be able to get a better indication of the powders at the surface of the Mars. So that's something that for us it's going to be working there in terms of the particle sizes. All right, so let's quickly move forward with the sieve analysis. You're familiar with this. Again, quickly, we're looking at 3 major sieves. Remember sieve number 3, or number 3-inch sieve, that basically would be the line in the sand between the gravels and the cobbles that we have, right? And then between number 4 and number 3, that would be the gravelly material. Between sieve number 200 and sieve number 4, you had the sandy material, and anything that passes sieve number 200, we call them fines, right? All right. Again, this is another way to look at the distinction or definition that we have. You're basically looking at weighing the soil that is retained on each of these sieves. The larger sieves are stacked at the top, and as you go down the stack, you see that the sieves are becoming smaller and smaller. So specifically for this one, for those of you sitting at the very back, it's sieve number 10, 20, 40, 50, this looks like 80 or 90, and the last one would be 200. So it basically becomes smaller and smaller as you go down the stack there. Typically for highway applications and foundation applications, we are looking at materials is smaller than 2 inches in diameter and going all the way down. So typically you might put in a sieve that corresponds to 1.5 inch at the top. All right, so all we talked about, it basically boils down to this plot. All right, so remember we are essentially mechanically shaking the sieves and measuring the weight on each of these sieves, right? And this is the table or the Excel spreadsheet that you have to set up for your sieve analysis. The first column and second column are repeating itself, so these are constant. The first one is sieve size, depending what sieve you have at the very top. Here we have sieve number 4 all the way to sieve number 200, and the last one is the pan, essentially when we collect the P200 material. The second column is sieve opening. You can read it right by the sieve, or you can also calculate that, but these are all given. That basically gives you the particle diameter that you want. The third column is the column that you basically have to do the measurements of weight on each of these sieves and record it in this table. Right. So the one that you basically have to populate here would be column number 3. The rest of it is just basically calculations based on it. Column number 4 is percent retained. Right. So what does that mean? It means that now I measured the weight that retained on each of these sieves. This means that 44 grams retained on the sieve number 10, 106 on seed number 80, 85 grams on seed number 200. That's basically what it means, right? And then what you have to do is essentially use the sum function in your Excel spreadsheet, right? SUM, and just do the calculation and sum all these cells that you have. So total would be 551 grams of soils. That would be the summation of what I have here. The next column would be percent retained, which is basically this weight divided by the total weight that I have. So for instance here it would be 44 divided by 551, that would be 8%. So that's basically what it means. And you basically move forward all the way down. And then you have, what is it? This is the fifth column. You're looking at cumulative retained, right? So what this means is that you have 0 here. 0 plus 8 would be 8. 8 plus 10 would be 18. 18 plus 15 would be 33. So basically you're looking at percent retained on that specific seed. The last one would be very simple and straightforward. That would be the cumulative passing, which would be 100% minus what you had in this cell. I specifically put these equations for you there so you can set up your Excel spreadsheet easily and essentially plot. So, what was my gradation curve? I had percent passing on the y-axis, right? And I had a log of diameter, right? So this is in log scale and this is in arithmetic scale, and this is essentially what you end up with. So that would be your gradation curve. Is it clear what we have here? So very simple and straightforward in terms of how